Welcome to another session of spectroscopy or analytical techniques. Today we'll understand about mass spectrometry. If you haven't subscribed yet, please do subscribe so that you don't miss such informative videos, and tap the like button if you like the video after watching. At the end of the session, you'll be able to state the principle of mass spectrometry, explain the instrumentation in detail and working of mass spectrometry, discuss the mass spectrum with an example, and list out the advantages, disadvantages and applications of mass spectrometry. First, let us understand the principle behind the mass spectrometry. Mass spectrometry is a technique used to identify the compounds present in the sample by vaporizing the sample into a mixture of gaseous ion with or without fragmentation. Next, sorting and separating the deflecting gaseous ions in the presence of magnetic field based on their mass to charge ratio and recording the relative abundance of each ion. That is, this analysis has three steps: ionization, where the sample is vaporized into a mixture of gaseous ions. That is, you have a molecular ion which can be further fragmented to smaller ions. So you will have many ions present which are separated by deflecting it in the presence of magnetic field based on the mass to charge ratio. This we call it as sorting and separation, which happens in the mass analyzer. Finally, it is detected and recorded as relative abundance of each type of ion, and which is done in detection and recorder. We'll see in detail the instrumentation part. Here we have three steps, that is ionization, where the sample is first injected through a sample injector. Here the sample can be vaporized externally and injected, or if it is a non-volatile liquid or a solid, it can be injected directly and vaporized inside the ionization chamber. That is, this part where the gaseous ions are converted to ions, we call it as ionization chamber. Here we require an electron beam source where we get a beam of electrons. When these beam of electrons bombards with the vaporized gaseous sample, it knocks out one or two electrons from it to give the charged ions. Mostly we get the cations, but we can also get anions, and we can analyze even the anions. But most of the mass spectrometers actually analyzes the cations. So these ions are focused in the form of a beam through the accelerating slits. Actually, here we have a series of accelerating slits varying with potential. The first accelerating slit will have nearly about 10,000 volts, and the last one will have 0 volts, and the intermediate slits will have the intermediate volts. And these beam of ions are focused through these accelerating slits, and then when it crosses this magnetic field, it deflects. That is based on the mass to charge ratio. The heavier ion will be deflected less and the lighter ion will be deflected more. So this way the separation occurs. So the step from this accelerating slits to this magnetic field, the deflection occurs, that is before it enters the detector. We call it as sorting and separating. Finally, these separated ions enter the detector, and the detector detects these ions and produces current proportional to the number of ions. And this is being recorded in the recorder as the relative abundance of each type of ion in the y-axis and m/z ratio, that is mass to charge ratio, on the x-axis. This is the instrumentation part. We'll see it in detail. That is, the inlet system, the sample is introduced and vaporized by heating. It can be vaporized externally and injected, or it can be injected and vaporized inside the system. That is the ionization chamber. And next is the ionization source. We have various types of ionization sources. Nearly 10 to 15 varieties are there. I have just shown 3. Here what happens is the sample molecules or atoms are ionized by knocking out one or more electrons. That is, when one electron is pushed out of a molecule, we get a molecular ion. And these ions can be further fragmented to smaller ions to form a mixture of molecular ions and the fragmented ions. Actually, one electron is normally pushed out, but if the energy of the beam of electrons which are produced in the ionization chamber is high, it can even push 2 electrons out. So commonly we get +1 charged ions, but sometimes rarely we get even +2 charged ions. And here these 3 types of ionization sources. One is electron bombardment, that is, electrons are generated in the glowing filament, bombards with the sample molecules and produces beam of ions. That is what we saw in the previous slide. Sometimes the atoms can be ionized when in contact with the heated metal surfaces such as platinum, tungsten, rhenium, tantalum, etc. These type of metal surfaces can be heated, and when the atoms are collides or comes in contact with this heated metal surface, it gets ionized. And direct current arc is plasma discharge. What is plasma is? It is the ionized gas with positive ions. That is, we said the mixture of gaseous ions are formed along with electrons, because the electrons are knocked out. Is produced when 2 electrodes are placed perpendicular to the axis of the electric field with high potential difference. That is, the potential difference can be between few hundred volts between the electrodes. And next is the accelerator. The ions are accelerated and focused as a single beam, as we saw in the instrumentation part, through the accelerating slits from a higher potential slit to the lower potential slit. And mass analyzer or separator, here is where the separation takes place. The ions are sorted and separated out based on the mass to charge ratio. This can happen with 2 different types of separators. Quadrupole separation occurs in the form of that is, with the combination of radio waves and DC electric fields, but the commonly used separator is magnetic sector, which we have seen in our instrumentation. This uses the magnetic field to deflect the ions based on the mass. More heavier the ion is, it will move less, and the lighter ions are deflected more. But if the charge is more, that is, in the denominator we have charge, the m/z ratio will become low if the charge is more. So it will be a lighter ion. So highly charged ions are deflected more than the low charged ions. That is, if we have +2 and +1, +2 charged ion will be deflected more than the +1 charged ion for the same ion. We should not take the fragmented ions. Okay. Next is the ion detector. We can use an electron multiplier, scintillation counter, or Faraday cup detector. It detects the number of ions entering the detector and produces electric current proportional to it. And lastly, the recorder. It records the relative abundance of each ion having specific mass to charge ratio to give a mass spectrum. That is, relative abundance of each ion is calculated this way. For a particular m/z ratio, the number of ions with that m/z ratio divided by the total number of ions detected, all types of ions put together which enters the detector, into 100 if you want to measure the relative abundance in terms of percentage. Here one more thing, if the number of ions entering the detector is more current is generated. If it is less current is generated in the detector. And we'll understand this with a mass spectrum of a very small molecule, that is carbon dioxide. When the beam of electrons bombard with the carbon dioxide molecule, it pushes one electron, that is knocks out one electron to produce CO2 plus one electron. That one electron is knocked out. So what is the m/z ratio for the CO2 plus? The molecular weight of CO2 is 44 and the charge is 1. So m/z is 44. So when the charge is 1, m/z as well as m value will be the same. And if the charge is 2, it will be 44 divided by 2 and it will be 22. This is how you should calculate. And nextly, one more thing, this m/z ratio 44, you have a peak corresponding to this 44, and we call this as the base peak, which is due to the molecular ion. This will always be the tallest peak because the molecular ion will be the first major bigger ion where only one electron is knocked out, and it will be 100% abundance because all the other fragmented ions are smaller ions which are broken from the molecular ion, and definitely the M by Z ratio of this fragmented ions will be very less compared to the molecular ion. So you should identify the base peak, that is the tallest peak, and see what is the molecular weight of it, and we can compare the compounds which has this molecular weight 44, and then go to the fragmented ion peaks. So this CO2 plus can be further fragmented to CO plus plus O or O plus plus CO. So here we have one cation plus neutral atom or a neutral molecule. So one cation plus one neutral atom or molecule. So it can also be fragmented as C plus and O2 molecule. So we have M by Z ratio 28, 16, 12, and we have corresponding peaks for 28, 16 and 12. So based on the spectral data of the fragmented ion peaks and the molecular ion peak, that is the base peak, we can determine this spectrum belongs to which particular compound. So it will be complex with the complexity of the molecule or the compound present. We can also have the mixture of compounds, but if you have the mixture of compounds, it has to be coupled with a chromatographic column like GC or HPLC, and it has to be separated, and then it has to enter the mass spectrometer. That is, you have GCMS, LCMS and so on. And there are various advantages of this method. Quick analysis, that is maximum of 1 to 3 minutes I can analyze up to 76 compounds or components. Okay, and it is reproducible, that is how many ever times I inject the sample, I get the same type of mass spectrum, and it can determine up to 16 to 76 components in just one stream itself. And disadvantages, because we are separating based on the M by Z ratio, it is difficult for us to distinguish the compounds having the same M by Z ratio. And similarly, the distinction between the isomers is also difficult because it will have the same M by Z ratio. This is the drawback and limitation of this method. And if you look at the applications, as we have already seen with an example of CO2, we can determine the molecular weight based on the base peak. You can determine the molecular structure, molecular formula from the mass spectral data and fragmentation pattern. And you can also distinguish between various isotopes of a given element, because different isotopes will have different mass. So based on the relative abundance, you can tell how much of each isotope is present in that particular element. And finally, based on all this data, you can also analyze proteins, peptides, lipids and oligonucleotides. Oligonucleotides only, not DNA, because DNA is a polynucleotide and it's very complex. So oligonucleotide means when you have the nucleotides, that is 20 to 30 nucleotides put together, we can analyze using mass spectrum, but it's not that viable and not that acceptable for determining the DNA or RNA structure. Okay, this is all for the session. Let us meet with another session. Until then, bye bye. If you haven't subscribed yet, please do subscribe and drop in your comments and tap the like button if you like the video. Thank you.